Welcome to our class. We'll continue on our convergence sequence. So here we are considering Cauchy sequence. So this is the definition of a Cauchy sequence in a metric space. We say that let S be a metric space. A sequence this in this S is said to be a Cauchy sequence, or we simply say that it's said to be Cauchy. If for any epsilon is greater than 0, there exists a number, positive number n, which is inside natural number, such that the distance between xm and xn will always be less than epsilon. For all this m and n is greater than this n in this place. So this is what we call a Cauchy sequence. So for instance now, sequence 1 over n is a Cauchy sequence. So the Cauchy sequence is the same thing as the sequence you are dealing with under the real analysis. Now let's consider a theorem under this Cauchy sequence. Now we have the theorem here. Every convergent sequence in a metric space is Cauchy. That is, every sequence that is convergent will be called Cauchy sequence. Now, to prove this, we need to look for a convergent sequence. So let's suppose that Sn converges to S. So if Sn converges to S, then by definition, if for every epsilon is greater than 0, there exists there exists this capital letter n greater than 0, such that distance between xn, x is less than epsilon for all n is greater than this. So we are dealing with this epsilon. If you are dealing with two numbers, we can simply write this thing. We can write this thing as this x is less than epsilon over 2, which is still the same thing for all n is greater than n1. So if you pick another thing, if you have another value here, m, we know that it will always converge to the same thing. So we say over 2 for all n is greater than n2. So we can have this. If it is convergent, we can write it in this format. Now let's consider this. We know that by triangular inequality, d of xm, xn, sorry, this place should be m. We are dealing with m here. Now by triangular inequality, we know that this one can be written as d of xn, x plus d of x, xn. So if you look at this, we have it here. This is epsilon over 2 plus epsilon over 2, which simply means that d of xm, this is strictly less than epsilon. So for all mn is greater than this n is the maximum of these two. So you will not discover that we express this Cauchy sequence in terms of these two convergent sequences. So in this case, we have seen that this convergent sequence leads to Cauchy sequence. Since we have this relationship, you see that it's the same relation of this Cauchy sequence. So in that case, we have shown that every convergent sequence is Cauchy. So another theorem. So before we consider the theorem, let's consider this definition. Subsequence. The definition is subsequence. Let's consider a sequence this in this metric space, and let this be a positive integer such that n1 is less than n2, like that. Then x of nk, snk subscript nk, is called subsequence of xn. So what subsequence simply means is that if you can get a sequence from a particular sequence, then that sequence is subsequent. That is what we are trying to say. For instance here, if you consider this, 1 over n. 1 over n is a sequence, which is same thing as 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, 1 over 8, and so on like that. Now, remember we can pick this even terms here. We can rewrite it as 1 over 2k, because if k is 1 to infinity, because if you put k here, 2 times 1 is 2, 2 times 2, when k is 2, 4, when k is 3, 6, like that. And also we can still deduce this there. This one will simply be 1 over 2, 1 over 4, 1 over 6, 1 over 8, 1 over 10, and so on. So you see that we got this from this place. Also, we can still get this 1 over 2 raised to power k. So k runs from 1 to infinity. This one is same thing as 1 plus 1 over 2 plus 1 over 4 plus 1 over 8. So like that, or you can say 1 over 16. It will be going like that. So this is another sequence. So we got this sequence from this place, and we also got this sequence from this place. So this is our SNK. So these two sequences, we call them subsequence of this sequence. Now let us now consider our theorem. Now the theorem: a Cauchy sequence Sn converges to a point if and only if it has a subsequence which converges to the same point S. What this theorem is trying to tell us is that if you have a sequence that converges to, let's say we have sequences, it converges to 3. Before you can say that this converges to, let's say, 3, it has to contain another sequence which converges to this 3 as well. So if you take this as an example, this sequence converges to 0. If you look at this one too, it converges to 0, and we know that this is a subsequence of this. If you look at this, it converges to 0 as well, because as this thing is going, the end point will be 0, as at this one too. So, and we know that these two sequences are subsequences of this sequence, and they both converge to the same point. That is what this thing means, that if a Cauchy sequence converges to a point, then it must have a subsequence which converges to the same point. So now let's prove it. So we start by saying let SNK be subsequence of Sn. So what do we want to show? What we want to show is that we want to show that if this Sn converges to S, then if and only if SNK converges to S as well. So what we now do is that we first assume that Sn converges to S. Then we show. So we need to show that SNK also converges to S. That's the first. Since we have if and only if, so we want to show that if Sn converges to S, then we need to show that SNK must converge to X as well. Now let's get on to the proof. So since we have assumed that Sn converges, so this one is very easy. The necessity of the proof is very easy, because since here we assume that this thing converges, so since we assume that it converges, then Sn is a subset of itself. We know that every set is a subset of itself. Definitely this Sn is a subsequent of itself, and we know that this one converges now, but Sn converges to S. So simply means that Sn will also converge to S. This one is a subsequence of this one. They are subsequence of each other. Our aim is to show that if Sn converges to S, definitely the subsequence of this thing must converge to S. Here we only assume here that Sn converges. They want to show that the subsequent also converges to this S again. But Sn, fortunately for us, Sn is a subsequent of itself. So definitely Sn converges. I've written it out. Since Sn is a subsequence of itself, hence Snk also converges. Because this Snk simply means subsequence. And this is subsequence of itself. So that about the proof. Now, we now prove the converse part. So we write it like this. Conversely, assume that Snk converges to S. Then we now show that Sn converges to S. That is, if a subsequence converges to S, definitely Sn will also converge to S. Now, since this thing Snk converges to S, we have assumed converges to X, then by definition, for all epsilon is greater than 0, there exists n greater than 0, so such that it will be distance of Snk comma X is less than epsilon. So you can say epsilon over 2 for all n is greater than capital N. So I can put n1 there. So I can decide to put ordinary epsilon there. So this is we only record this thing by definition. Now, this Sn we are talking about is a Cauchy sequence. Then, by definition of what? By definition of Cauchy sequence. Also, for every epsilon is greater than 0, there exists, let's say, n2 greater than 0, such that we say that this one is distance of m comma distance of n. I can say that is less than epsilon over 2 for all m n is greater than n2. So this is definition of Cauchy sequence. Then we apply triangular inequality. The triangular inequality we want to apply is this. We know that this, if you want to apply, it's the same thing as d of xn comma snk plus d of snk comma x. This will strictly be less than, if you look at this here, it's just the same thing. Snk and all this, they are just the same thing. This is epsilon over 2. This one is epsilon over 2. And that simply means that d of Sn comma this is less than epsilon if you add it together. So for all n is greater than capital letter N. Don't forget that this capital letter N is maximum of n1 and n2. So if you have this type of relationship, this thing simply means that Sn converges to X, or we say that, or we write Sn this. So we have now shown that if Snk converges to S, then Sn also converges to S. And if you look at how we started, so since Snk converges to S, so by definition we must have this. But instead of, in the definition we put ordinary epsilon. Here we are dealing with two things, so we need to use epsilon over 2. So we are still on the line. So this is by definition, and I put n1 here. Also, Sn is a Cauchy sequence by the theorem. The theorem says that this is the theorem here. A Cauchy sequence converges to a point. So that is why we said that since this one is a Cauchy sequence, where is it? Okay, since this one is a Cauchy sequence, that is by the theorem. So we now go by definition of Cauchy sequence. That is why we wrote then by definition of Cauchy sequence. For epsilon epsilon is greater than 0, we have this by definition of Cauchy sequence. So our aim is to bring ordinary Sn out. So we now apply triangular inequality here, which is same thing as we just need to bring snk to these two, to the middle of these two. It will now be Sn comma snk plus snk comma s. This one is just the same thing as this. This one is the whole of this is representing by m, which is epsilon over 2. This one is here, is epsilon over 2. So adding it together, we have this. So and whenever we have this type of relationship, it means the sequence converges to this point S, and we write it. So and that completes the proof. Another important definition here is a complete space or complete metric space. So we say that a metric space this is said to be complete if every Cauchy sequence in that metric space converges to a point in that metric space. Every Cauchy sequence in it converges to a point in it, then that metric space, that space is said to be a complete space, or the metric space is said to be a complete metric space. So the set of real number, set of complex number are all complete. So let's move to another important definition. A subspace. Let S comma D be a metric space and let A be a subset of S. So we call A subset, we call a subspace of this metric space if A itself is a metric space under this metric D. So that is the meaning of subspace. So if a subset of a metric space is again a metric space, then we call that subset a subspace. So let's consider the following lemma. So we have the lemma, I will state the lemma without proof. Let set A is closed if and only if a sequence in it, this sequence, converges to a point in A, then we say that A is closed. So with this lemma, it leads us to the following theorem. Now, the theorem. Every subspace of a complete metric space is complete. That is, every subspace A of a complete metric space X is complete if and only if A is closed in X. So what we do is that since we have if and only if, so we first assume that A is a complete metric space, then we show that A is closed. Which is this? Now, we have assumed that A is complete. So we cannot say that since A is complete, we know that by definition of a complete metric space, that every convergence, every Cauchy sequence in it converges to must converge to a point in it. So since A is complete, so we know that there exists a sequence this, so which converges to X in A. So by definition, we know that when the space is complete, then every convergence sequence, every Cauchy sequence in it will converge to a point in it. And we know that this convergence sequence is a Cauchy sequence. So we cannot write that this Xn converges to a point in A. Why? Because by definition, every Cauchy sequence in it must converge to a point X in this. So S is in A. So this is by definition. We must have a sequence which converge to this. And we know by the theorem we stated, by the lemma we stated, we said that A is closed if the sequence in it converges to a point in it. So you will now see that, so let me put here, since if A is closed, since A is closed, if the sequence in it converges to a point in it. So you now see that this sequence in A now, it converges to a point in A. So why so? Because we have concluded here that A is complete. So in that case, if it happens like that, we now say that A is closed. So we have shown that A is closed. Now we now assume that A is closed. We show that A is complete in next. That is it. We first assume that A is closed. Then we show that A is complete in next. Now, since we have assumed that A is closed, since A is closed, definitely we must have a sequence. So there exists this sequence that converges to X in A. So that simply means that this must converge to X in A. But Xn is a Cauchy sequence. Why is it a Cauchy sequence? On this one, we don't assume that it's a Cauchy sequence here. It's just a sequence. But it's not a sequence that converges to a point in it. But we have said there, you have said before that every convergence sequence is Cauchy. Here, we only assume that there is a sequence that converges to a point in A. So definitely that sequence must be a Cauchy sequence. So in that case, we cannot say that since A is closed, we cannot conclude that since A is closed, there exists a Cauchy sequence. There exists a Cauchy sequence which should converge to X in A. But remember that A is a subset of X. So definitely the Cauchy sequence this must also converge to a point in X, because A is a subset of X and the Cauchy sequence converge to A. So you cannot see that this is just a definition of a complete metric space, which says that every Cauchy sequence in it converge to a point in it. So since the Cauchy sequence converge to a point in X, so this simply means that A is closed in X, and that completes our proof. Sorry, it is not closed. It is, we say A is complete in X. So that's how to complete something, because we want to show that A is complete. That's what we are doing. So that completes the proof.